Imagine something moving faster than the physical world around it. I don't mean light and I don't mean sound. I mean information.
Right.
Before your finger physically taps a screen, before your vocal cords even vibrate to say hello, even before you consciously realize you're looking at a sunset, a signal has already raced through your body.
It's the biological equivalent of a fiber optic cable. It really is. But instead of light, it's using salt water and protein.
And no electrons.
No electrons.
It's using ions, charged particles.
Exactly. It's the spark. We tend to think of our bodies as these, mechanical things, levers and pumps, muscles and bones. But at the most fundamental level, before any of that mechanics can happen, we are electric.
We are.
And today on this deep dive, we are going to decode that electrical infrastructure. We are going to find out how a bag of water basically manages to generate a voltage.
And we aren't just going to memorize definitions today. That's not the goal. We're effectively going to build a neuron from the ground up.
The mission here is to understand how physiology literally speaks in voltage. Because if you don't understand the nerve, you don't understand the brain, you don't understand the heart, or, frankly, how you are even listening to this right now.
To do that, we have pulled two absolute heavyweights from the shelf. We are synthesizing what medical students everywhere call the Bibles of physiology. Ganong's review of medical physiology and the legendary Guyton and Hall textbook of medical physiology.
It's a really powerful combination, and they serve different roles in this. We're leaning on Ganong, specifically the chapter Excitable Tissue, Nerve, for let's call it the cellular nuts and bolts.
The hardware.
The hardware, exactly. Ganong is fantastic for the structural details, the transport systems, the support cells, the glia. It really gets into the molecular nitty-gritty.
And then we have Guyton. We're focusing on membrane potentials and action potentials. And if you know Guyton, you know this is where we get the systems thinking, the physics.
This is the manual on the battery that powers the cell.
Yeah.
It's the heavy math behind that spark.
It is.
And just a quick disclaimer before we wire the system up. What we are doing here is a conceptual synthesis. We're building a map. This does not replace reading the texts.
Absolutely not.
If you are prepping for exams or for clinical practice, use this conversation to scaffold your revision. But you still need to open the book. We want to give you the why so the what sticks a lot better.
Exactly. Think of us as the architects showing you the blueprints. You still have to go and lay the bricks. So let's start with that hardware. If we're building a machine that transmits information, we need a physical structure. But Ganon makes a point here that I think is really helpful.
I know what you're going to say.
It moves away from just naming parts and starts talking about functional zones.
Right. Which is so much more useful. It's tempting to just say dendrite, soma, axon, terminal, and move on. But that misses the entire point. The neuron is a specialized input-output machine. So Ganon breaks it down by what the parts do.
Okay, so let's start with zone 1, the receptor zone.
This is usually the dendrites and the soma, which is the cell body. Ganong uses a beautiful phrase here, dendritic arborization.
Arborization, like an arboretum,
Yeah.
like trees.
Exactly. Visualize a coral reef or a massive oak tree with thousands upon thousands of branches stretching out. That's your dendritic tree. Its whole job is surface area. It needs to catch signals. A single motor neuron in the spinal cord might have thousands, sometimes tens of thousands of these little synaptic contacts on its dendrites.
So it's basically a giant net. It's just catching information from all over the place.
An antenna array.
An antenna array, I like that. And all of that information funnels down into the soma.
The soma, or the cell body. And this is the metabolic center. This is the factory. It houses the nucleus, the DNA, the mitochondria, the ribosomes. It's where all the proteins are built to keep the whole cell alive. This is, pretty standard cell biology so far.
But then we get to the transmission line, the axon. And this is where the scale of biology gets absolutely mind-boggling. I think people really struggle to visualize just how geometrically weird neurons are.
They are completely absurd structures. You're right. The axon originates from a sort of thickened part of the cell body called the axon hillock. But the length, you really need to try and visualize this. If the cell body were the size of a tennis ball sitting on your desk,
Okay.
the axon of a motor neuron running from your spine to your foot wouldn't just be a few feet long. On that scale, it would be like a garden hose stretching for a kilometer or more.
That is just, it's a massive distance for a single cell to manage. Usually you think of cells as these compact little spheres.
Yeah.
This is a tube that is thousands, maybe millions of times longer than it is wide.
It's an engineering marvel. And the most critical part of this whole transmission line, functionally speaking, is the very, very beginning, the initial segment of the axon right after the hillock. Ganong highlights this as the integration center.
The decision point.
The decision point. This is usually where the action potential, the spark, is actually generated.
Why there? Why not in the middle of the axon?
Huh.
Or why not back in the cell body itself?
Because that initial segment is biologically tuned to be, well, trigger happy. It is packed, absolutely saturated, with voltage-gated sodium channels. It has a significantly lower threshold for firing than the rest of the cell body.
So it's more sensitive.
Much more sensitive. So the soma might get 100 weak signals, a little noise here, a little whisper there. The soma and dendrites kind of ignore them, but the initial segment is the judge. It sums all of them up. And if the total noise, the total voltage change, crosses a certain line, the initial segment pulls the trigger.
So it's the ultimate signal from noise separator.
Precisely. And then finally, at the very end of that long line, we have the output zone. The presynaptic terminals, sometimes called boutons. These are the little button-like endings where the electrical signal gets converted back into a chemical signal, the neurotransmitter, which then crosses the synapse to the next cell.
Okay, so we have the receiver, the factory, the wire, and the output, the whole system. But I want to go back to that garden hose analogy. It's a great visual, but it raises a huge problem. If the axon is a meter long, and all the proteins are made back in the factory, in the soma.
Yeah.
How on earth do supplies get to the end of the line?
Yeah.
You can't just float them downstream. Diffusion over a meter would take years.
Decades, maybe longer. It's a massive logistics problem. If you relied on simple diffusion, the nerve ending in your big toe would die of starvation before a single protein made in your spine ever reached it.
So how does it solve it?
So Ganong covers this in great detail. It's called axonal transport. The cell effectively has a railway system running inside the axon. The tracks are made of microtubules.
It has little trains running on the tracks.
It has molecular motors, proteins that literally walk along the tracks carrying cargo. And when I say walk, I mean it physically. We have electron microscopy videos of this now. It's incredible.
Wait, like with legs. It's not just a metaphor.
Not a metaphor. They have two globular heads that act like feet. They bind to the microtubule, they hydrolyze ATP, they burn fuel, and they swing one head past the other. It looks like a little stick figure carrying a massive backpack just trudging down a road.
That is just, it's unbelievable engineering. So let's break down the shipping schedule. You've got stuff going out and stuff coming back, right?
Correct. The outbound shipping is called orthograde transport. Ortho means straight or correct, so it's moving forward from the soma out to the terminal. The motor protein that does this is called kinesin.
Kinesin. I always picture it like a kinetic engine, something that drives forward.
That's a great way to remember it. Kinesin moves along the microtubules towards what's called the positive end, which is out at the terminal. And Ganong notes there are two distinct speeds. There's fast axonal transport.
How fast is fast?
It moves at about 400 millimeters per day.
400 millimeters. So 40 centimeters. That's, well, on a cellular scale, that is supersonic.
It is. That's for things that are needed urgently. Synaptic vesicles, mitochondria for energy, enzymes that manage neurotransmitters. The cell brings a lot of ATP to keep this fast lane moving.
And then there must be a slow lane.
The slow lane, slow axonal transport. This is more like 0.5 to 10 millimeters per day. It's a crawl.
What's it carrying?
This is more like the structural drift. It involves the movement of the cytoskeleton itself, things like neurofilaments and tubulin components. They just kind of ooze down the axon to maintain its physical structure. It's like the road paving crew compared to the ambulance in the fast lane.
I see. Okay, so kinesin takes things out. What brings things back? Because you have to recycle, right? You can't just pile up garbage at the nerve terminal.
You absolutely have to. That process is called retrograde transport. Moving backward, the motor protein here is a different one. It's called dynein. Dynein moves at about 200 millimeters per day, so it's pretty fast. It picks up used vesicles for recycling, or, very importantly, chemical signals from the target cell, like nerve growth factor, and hauls them all the way back to the soma.
We'll talk more about nerve growth factor, or NGF, later, but that's basically the we are still connected and alive signal, isn't it?
It is the confirmation receipt. It tells the nucleus, the connection is good, don't initiate the self-destruct sequence. But Ganong throws in a detail here that is genuinely unsettling. This beautiful, efficient railway system, it isn't just used for recycling. It creates a massive vulnerability.
This is the Trojan horse mechanism.
It is. Several viruses have evolved specifically to hack this transport system. I mean, think about rabies.
Right.
If you get bitten by a rabid animal, the virus enters the nerve endings at the muscle or the skin. But the virus doesn't want to stay in your foot. It needs to get to your brain to replicate and drive you mad so you bite someone else to propagate itself.
So it just hops on the dining train.
It binds specifically to the transport machinery. It hitches a ride on dinin, travels all the way up that long axon retrograde to the cell body in the central nervous system. Herpes simplex does the same thing.
The cold sore virus?
Exactly. It retreats up the nerve to hide in the soma, where the immune system can't get it, and then it rides back down the Kinnison tracts to cause a cold sore when you're stressed or run down.
Wow. That puts the whole idea of latency for those viruses into a physical perspective. They aren't just floating around in your blood. They are physically retreating up the logistics line into the fortress of the cell body. It's using our own anatomy against us.
It's horrifyingly ingenious. Evolution finds the vulnerability in every single system.
Okay, so that's the hardware. We have the structure, we have the logistics, the tracks, the trains, but a wire is completely useless without a current. We need to talk about the battery.
The resting membrane potential. And this is where we really need to switch our primary focus over to Guyton, because he explains the physics of this so beautifully.
And this is usually where students' eyes, including mine, start to glaze over. So let's try to make this as concrete as possible. The concept is that before a nerve can fire, it has to be charged, right?
Yep.
It's not just sitting there at 0 volts.
Not at all. If a neuron were at 0 volts, it would be dead. Equilibrium is death in biology. A living neuron at rest is a loaded spring. It has a voltage difference across its membrane, and typically that's about minus 70 millivolts inside relative to the outside.
Negative 70 millivolts. That's the magic number we all have to memorize. But I want to challenge this for a second. We're talking about salt water. We don't have electrons flowing through copper wires.
Yeah.
How in the world do you get electricity out of soup?
That is the fundamental question, and it comes down to what Guyton calls diffusion potentials. It's a tug of war, a constant battle between two fundamental forces: concentration, which is diffusion, and electricity, which is charge.
Okay, set the scene. Who are the players in this tug of war?
We have ions-charged particles. The main players are sodium, which is Na+, and potassium K+. We also have large anions, which are negatively charged proteins stuck inside the cell, but let's focus on the moving parts. The cell creates a gradient. Inside the cell, you have a massive concentration of potassium. Outside the cell, you have a massive concentration of sodium.
Okay, so potassium is packed inside like commuters on a rush hour subway car. It wants out.
It desperately wants to leave. It wants to diffuse out, down its concentration gradient, from high concentration to low. Now, imagine the cell membrane has little holes in it, channels, that only let potassium through. What happens?
Potassium starts to leave the subway car.
It starts to leave, but, and this is the absolute key physics point, potassium is a positive ion. It's K+. As it leaves the cell, it carries that positive charge with it to the outside.
So the inside is losing positive charge, which means the inside is becoming negative.
Correct. And as the inside becomes more and more negative, it starts to electrically pull the positive potassium back in. Opposites attract.
So there's a tug of war.
There it is. The concentration gradient is pushing potassium out, but the developing electrical gradient is pulling it back in.
And eventually, those two forces balance out.
Eventually, they reach a perfect equilibrium. When the push of diffusion equals the pull of electricity, the net movement of potassium stops. The voltage at which that happens is called the Nernst potential.
The Nernst potential.
And Guyton gives us the math. If the membrane were only permeable to potassium, that perfect balance point, where the exit force equals the entry force, would be at minus 94 millivolts.
Okay, minus 94, that's the potassium dream voltage.
That's its ideal voltage, precisely. Now let's look at sodium. Sodium is high outside the cell. It wants to rush in. And since the inside is negative, it's also being pulled in electrically. Both forces are pointing inwards.
So if you opened a sodium door,
it would flood in. It would rush in until the cell was positive enough inside to start pushing it back out. The Nernst potential for sodium is positive 61 millivolts.
Okay, this is the crux of it. We have a massive tug of war. Potassium is pulling the cell's voltage towards minus 94. Sodium is pulling it towards positive 61. But the actual resting potential is minus 70. Why does potassium get so much closer to its dream? Why does it win?
This is where we need to upgrade from the Nernst equation to the Goldman equation. The Nernst equation is for a single ion in a perfect world. The Goldman equation accounts for the messy reality that the membrane is dealing with multiple ions at once. It's essentially a weighted average calculator.
Weighted by what? What's the weighting factor?
Permeability. How easily can the ion cross the membrane? Imagine a voting system. Sodium gets a vote for plus 61. Potassium gets a vote for -94. But this is not a democracy where everyone gets one vote.
Potassium has more voting power.
Potassium has superdelegate because at rest, the cell membrane is about 100 times more permeable to potassium than it is to sodium.
Wait, 100 times? That's a huge difference.
A massive difference. And Guyton emphasizes this. There are these special channels called leak channels, specifically tandem pore domain K+ channels, that are just open at rest. It's like a room with 100 large doors open for potassium to leave and only one tiny microscopic crack for sodium to sneak in.
So potassium's vote counts 100 times more than sodium's. That explains everything. It explains why the resting potential, -70, is so much closer to potassium's equilibrium of -94 than it is to sodium's.
Exactly. The Goldman equation just formalizes that intuition. The resting potential is rigged by the membrane's permeability. The leak dictates the voltage.
Okay, I have to clarify a massive misconception here because I know I was taught this wrong initially. I remember being told that the sodium-potassium pump creates the potential. You know, the pump moves 3 sodiums out and 2 potassiums in. That's moving charge, right? Doesn't that create the -70?
I'm so glad you brought that up because that is probably the single most common error students make, and it's completely understandable. The pump is electrogenic, meaning, yes, it does create a net charge difference. If I give you $2, the 2K+, and you give me $3, the 3 net plus, I am losing $1 on every transaction. The cell is losing a net positive charge.
So it does contribute something.
It contributes, but Guyton calculates that this direct electrical contribution is tiny. It's only about -4 millivolts.
-4 out of -70.
Ah.
So directly, the pump is barely doing anything to the voltage.
Directly, yes. But indirectly, it does everything. The pump's primary job is not to create the voltage. It's to create and maintain the concentration gradients. It fills the tank with potassium inside and pumps the sodium out. It loads the gun.
And the leak is what fires it.
The leak of that potassium through its channels is what actually pulls the trigger and generates the bulk of the voltage.
That is such a crucial distinction. The pump builds the hill. The leak creates the hydroelectric power as the ions roll down.
Precisely. And if you stop the pump, say, with a metabolic poison, the potential doesn't crash instantly. It fades away slowly as the gradients run down over minutes. But if you could magically block the leak channels, the potential would vanish in a microsecond.
This leads us perfectly to a fascinating clinical application that Gannon highlights in one of its clinical boxes. Since the battery depends so heavily on that potassium gradient, what happens if you mess with the potassium levels in the blood?
This is the danger of hyperkalemia high potassium and hypokalemia low potassium. This is not just textbook theory. This is life-threatening.
Let's walk through the logic. If I have hyperkalemia, so high potassium in my blood, outside the cell, what does that do to our tug of war?
Well, normally potassium wants to leave the cell because the concentration outside is very low.
Right.
If you raise the level outside, the difference between inside and outside becomes smaller. The gradient is weaker.
So potassium doesn't want to leave as badly. There's less of a push.
Exactly. Less of it leaves. That means more positive charge stays inside the cell. So the resting membrane potential becomes less negative. It might go from -70 millivolts up to, say, -60.
So this sounds, I don't know, beneficial. It's closer to 0. Isn't that good?
It's closer to the threshold for firing. It makes the nerve more excitable. That sounds good for a second until your heart muscle becomes so excitable that it goes into a fatal arrhythmia and stops pumping effectively. The cells become twitchy.
Yikes. Okay, so hyperkalemia equals twitchy, spastic, dangerous excitability.
In the early stages, yes. Now let's flip it. Hypokalemia, low potassium in the blood.
Now the gradient is huge. The difference between inside and outside is even bigger. Potassium rushes out even faster.
Correct. More positive charge leaves the cell than normal. The cell becomes hyperpolarized. The voltage drops to -80 or maybe even -90.
So it's much further away from that firing line.
Much, much harder to fire. The result is weakness, paralysis, delayed reflexes. You see this in patients with kidney issues or severe diarrhea and vomiting. The physiology of the Nernst equation is literally dictating their symptoms at the bedside.
That is wild. It connects the abstract math directly to a patient's physical exam. Okay, so we have our battery. It's charged to -70 millivolts. The system is primed. The archer has the bow drawn. Now we need to let the arrow fly.
The spark.
The action potential.
The action potential. This is the universal language of the nervous system. It is how a thought travels, how a pain signal reaches your brain. And the most important thing to understand about it first is that it is an all-or-none event.
I always go back to the toilet flush analogy for this one.
It's the best analogy there is, honestly. You can jiggle the handle a little bit. That's a subthreshold stimulus, and nothing really happens. Maybe a little water moves in the bowl, but just settles back down. But if you push that handle past a certain point, the threshold, the mechanism engages, and you get the full, complete flush.
And crucially, pushing the handle harder doesn't make it flush harder.
Right.
Once it goes, it goes. A neuron fires, or it doesn't. There's no such thing as a half fire.
Exactly. In the neuron, that threshold point is usually around minus 55 millivolts. If a stimulus comes along and pushes the voltage from minus 70 up to minus 55, the voltage-gated sodium channels trigger.
And this is where Guyton describes that incredible positive feedback loop, the Hodgkin-Huxley cycle.
Yes. This is the explosion. At minus 55 millivolts, the activation gates on the sodium channels flip open. Sodium, which is high outside, rushes in. Since sodium is positive, this makes the inside of the cell more positive. That voltage rise causes more sodium channels to open, which lets in even more sodium.
It's a runaway train. An avalanche.
It's an avalanche. The permeability of the membrane to sodium increases by something like 500 to 5,000-fold in a fraction of a millisecond. The potential just shoots up past zero all the way to about positive 35 millivolts. This is the depolarization phase, the upstroke.
We've completely reversed the polarity. The cell is now positive on the inside. But obviously we have to reset. We can't just stay positive forever.
Right. We need repolarization, the downstroke. And this is where the genius engineering of the channel protein gets really cool. The sodium channel has a built-in timer.
This is the double gate mechanism that Guyton talks about, right?
Yeah.
This can be a little tricky to visualize.
It can. So let's imagine the sodium channel is a tunnel through the membrane. It has two separate doors, an activation gate on the outside and an inactivation gate on the inside.
Okay. Walk us through the choreography of these gates in slow motion.
At rest, at minus 70 millivolts, the activation gate on the outside is closed, but the inactivation gate on the inside is open. It's like a door that is shut but unlocked.
Got it. Closed but ready.
When we hit threshold minus 55, the activation gate flips open almost instantly. Bam! The tunnel is open, sodium rushes in, that's the spark.
But then what happens?
That same voltage change, that depolarization, also triggers the inactivation gate to close. But, and this is the whole key to the timing, it is slow. It's like a heavy ball and chain attached to the inside of the channel. It takes a fraction of a millisecond for it to swing shut and plug the hole.
So for that tiny split second, both gates are open. The fast activation gate is open, and the slow inactivation gate hasn't closed yet.
Yes, that's the window. That's when the sodium floods in. But then, clunk, the inactivation gate slams shut, the tunnel is blocked from the inside, sodium influx stops, the spark kills itself.
And at the same time, all of this is happening, the potassium channels are just starting to wake up.
Yes. The voltage-gated potassium channels are also slow responders. They were also triggered at minus 55, but they take their time. Just as the sodium door is slamming shut, the potassium door finally swings wide open.
And potassium, as we know, wants to leave.
And now the cell is positive inside, at plus 35. So potassium really wants to leave. It's being pushed by its concentration gradient, and now it's also being repelled by the positive charge inside. It floods out of the cell, carrying positive charge away, and that plunges the voltage right back down.
That's the downstroke, the repolarization.
Yes. In fact, the potassium channels are so slow to close that a little bit too much potassium leaves. The voltage actually dips below minus 70, maybe down to minus 75 or 80. This is the after hyperpolarization. It overshoots the landing a bit.
This intricate timing of the gates, the fast sodium opening, the slow sodium closing, the even slower potassium opening, it explains something else that's really important. It explains why the signal only goes one way. Why doesn't the fire spread backwards down the axon?
The refractory periods. This is absolutely vital for directional signaling. When that sodium channel's inactivation gate, the ball and chain is shut, it cannot be reopened by voltage. It doesn't matter how much you stimulate it. It has to wait for the membrane to repolarize back to rest before it resets.
Wow.
This is the absolute refractory period.
The toilet is currently flushing. You cannot push the handle and make it flush again.
You cannot. This ensures the action potential can't turn around and go backwards. The membrane immediately behind the propagating spark is dead for a moment.
Right.
It forces the signal to move forward into fresh, excitable territory.
Then after that, there's the relative refractory period.
Right. This is when the sodium channels have reset. The ball and chain has dropped away. But those slow potassium channels are still open and the cell is hyperpolarized, down at minus 80. You can fire the neuron again, but because you are starting from a deeper hole and you're fighting against the outgoing current of potassium, you need a much stronger stimulus to reach threshold.
So it acts as a filter. It prevents the brain from just seizing up with random high-frequency noise.
Exactly. It paces the firing rate and ensures signals are meaningful.
Okay, so we've generated the spark at the initial segment, but a spark in my spinal cord does me no good if it doesn't get to the muscle in my foot. We need propagation. We need to move the signal down that long, long wire.
And the axon acts like a wire. But again, biology faces a problem. Biological wires are, frankly, terrible. They are leaky, they have high resistance and high capacitance. The signal would fade to nothing over a very short distance unless we constantly boost it.
This brings us to conduction velocity. What determines how fast that signal moves?
Two main variables, just like with an electrical wire: diameter and insulation.
Diameter seems pretty straightforward. It's just simple physics, right?
Mm-hmm.
A wide hallway is easier to run down than a narrow one.
Exactly. It's about internal resistance. A wider axon has less resistance to the flow of ions down its center, so the current can spread further and faster. So a wide axon conducts faster. But biology has a space problem. If we made all our axons huge to get the speed we need, our spinal cord would be the size of a telephone pole.
Not practical. So we need option B, insulation.
Enter myelin. This is one of the greatest evolutionary leaps in the entire vertebrate nervous system. Myelin is a fatty sheath that is wrapped around and around the axon. In the peripheral nervous system, the PNS, it's made by Schwann cells. In the central nervous system, the CNS, it's made by oligodendrocytes.
And Ganong describes this wrapping process. It's not just a coating. The glial cell literally wraps its own membrane around the axon over and over again, like a roll of electrical tape.
Up to 100 layers thick. It's made of a lipid called sphingomyelin, which is a potent electrical insulator. But to understand why this works so well, we have to talk about a concept called capacitance.
Oh boy. Physics alert. Break this down for us.
It sounds scary, but it's not. Think of the cell membrane as a capacitor. It's two charged plates, the positive ions outside and the negative ions inside, separated by a very thin insulator, the membrane itself. Because that wall is so thin, the positive charges on the outside are strongly attracted to the negative charges on the inside. They are kind of holding hands through the wall.
Okay, I can picture that.
To change the voltage, to depolarize the membrane, you have to break that attraction. You have to move a lot of ions to overcome that stored charge. That takes time and energy.
And myelin adds distance between the plates.
Exactly. Myelin dramatically thickens the wall. It moves the positive and negative plates much further apart. The charges can no longer feel each other as strongly. The capacitance drops precipitously. This means it's much, much easier and faster to change the voltage in that region.
So the electrical signal can just zip through the myelinated sections of the axon.
Almost instantaneously. But that passive signal would eventually die out if we didn't boost it, and that's why we have the nodes of Ranvier. These are tiny, uninsulated gaps in the myelin occurring every millimeter or so. The bare axon membrane is exposed there.
And this is where the magic happens.
This is the trick. The voltage-gated sodium channels are not scattered evenly along the axon. They are almost exclusively concentrated at the nodes.
How concentrated are we talking?
The numbers from Ganong are staggering. In an unmyelinated nerve, you might have about 100 channels per square micrometer. At a node of Ranvier, you can have up to 12,000.
Wow. So the nodes are these supercharged relay stations.
That's a perfect description. So the electrical current is generated at one node. It shoots passively and very quickly down the insulated tube, the internode where capacitance is low, and it hits the next node. The voltage change there easily triggers those 12,000 channels, which causes a massive new influx of sodium boom, a new fresh action potential, which then shoots the signal down to the next node.
Saltatory conduction. From the Latin saltare, meaning to dance or to jump.
Yes. The action potential literally jumps from node to node, and this does two incredible things. One, it is incredibly fast. Myelinated fibers can conduct at up to 100 meters per second or more. Two, it is incredibly energy efficient. Because you only have ion exchange happening at the nodes, the Na plus K plus pump has much less cleanup work to do. It saves a huge amount of ATP.
Efficiency is always key in biology. Now, Ganong has a whole classification system for nerves based on this. The alphabet soup of nerve fiber types, A, B, and C.
It's a hierarchy of speed and function.
At the very top, we have the type A alpha fibers.
The Formula One cars of the nervous system, These are the widest, most heavily myelinated fibers. They conduct at 70 to 120 meters per second. That's nearly 300 miles per hour.
And what kind of information is worthy of that kind of speed?
Proprioception, your sense of where your body is in space, and somatic motor commands to your skeletal muscles. If you start to trip, your brain needs to know instantly where your ankle is so it can send an immediate direction. You can't wait for a slow signal.
That makes perfect sense. Then we go down the list to A delta.
Smaller, a bit less myelin. They conduct at about 12 to 30 meters per second, still very fast. These carry fast pain and temperature, the sharp, immediate prick of a needle.
And then at the very bottom of the ladder, we have type C fibers.
The unmyelinated narrow country roads. They creep along at 0.5 to 2 meters per second, basically walking speed. These carry slow pain, that throbbing, aching sensation that comes later, and many autonomic functions.
It's amazing to think that when you stub your toe, you actually feel the sharp impact first.
Yep.
That's the A delta signal arriving. And then a second or two later, the deep throb sets in. That's the C fiber signal finally getting there. You are literally experiencing the difference in conduction velocity.
You are perceiving the physics of your own nerves in real time.
There is a really practical clinical application of this that everyone who's been to the dentist has experienced. Local anesthesia.
Yes. Drugs like lidocaine work by blocking voltage-gated sodium channels. If sodium can't get in, the nerve can't fire an action potential. Simple as that. But here's the nuance that Ganong points out. These drugs affect the different fiber types in a very specific order.
The order of susceptibility.
Small, unmyelinated fibers are the most susceptible to the block. So the C fibers get knocked out first. You lose the sensation of that slow, aching pain first. Then the A deltas go. So you lose sharp pain.
But you can still feel the dentist pushing and vibrating your jaw.
Exactly, because the large, heavily myelinated A alpha fibers that carry pressure and motor signals are the last to be blocked. They have such a huge safety factor and surface area. So you end up in that weird state where you feel the pressure, but not the pain. It's a very specific chemical dissection of sensation.
Yeah, contrast that with when your leg falls asleep. Saturday paralysis, as they sometimes call it.
Compression blocks nerves in the opposite order. Physical pressure affects the large myelinated fibers, the A alphas first. They are more physically vulnerable to being squashed and having their blood supply cut off. So if you sleep on your arm, you lose motor function, and the sense of touch, the arm feels heavy and numb, but the small C fibers carrying pain might still be working perfectly fine.
That is a great party fact. Lidocaine kills the small guys first. Pressure kills the big guys first.
Precisely.
Let's pivot now to the support staff. We focus so much on the neurons, but they're actually outnumbered by the glial cells, the glue.
And for a very long time, we thought they were just that packing peanuts for the brain, just structural filler. But Ganong makes it very clear they are active, dynamic partners in neural function.
We've already mentioned Schwann cells and oligodendrocytes, the myelin makers in the PNS and CNS, but let's talk about the others. Microglia.
Microglia are the resident immune system of the central nervous system. They are effectively specialized macrophages. They are the scavengers. They crawl around, hunting for cellular debris, damaged cells, or invading pathogens. Interestingly, they don't originate in the brain. They actually migrate in from the bone marrow during development.
And then there are the astrocytes. These are the stars of the show. Literally, they're star-shaped.
They are the most abundant glial cell by far. And they do almost everything. They form the structural lattice of the brain. They wrap their little end feet around capillaries to help form the blood-brain barrier, which is critical for controlling what gets from the blood into the brain's environment. And they also act as chemical janitors.
Janitors, how so?
When a neuron fires, it releases potassium into the small space outside the cell. And when a synapse is active, it releases neurotransmitters like glutamate. If that stuff just piled up, the neuron would short circuit. Remember our hyperkalemia issue? Astrocytes have pumps that actively suck up that excess potassium and glutamate to keep the environment clean and stable for the next signal.
That is a vital, underappreciated role. Now, I want to talk about something Ganong discusses that feels almost poetic. The neuron's will to live, neurotrophins.
This concept really changes how you view the brain. We used to think neurons just grew and then stayed there. But it turns out neurons are constantly asking the question, am I needed? Is my connection useful?
And if the answer to that question is no,
they commit suicide. They initiate a programmed cell death pathway called apoptosis.
That's brutal.
It's ruthlessly efficient. During development, a neuron reaches out and tries to connect to a target, like a muscle fiber or another neuron. If it makes a successful connection, the target cell releases a chemical blessing, a neurotrophin, the most famous of which is nerve growth factor, or NGF.
And this NGF is then shipped back home.
It's picked up by the nerve terminal and shipped all the way back up the axon via that retrograde dynein transport we talked about. It goes all the way to the nucleus and delivers the message. We made it. We are connected. Keep the lights on.
And if they don't get that NGF signal?
The cell dies. But Ganong adds a really twisted detail here about the receptors for these factors. There are two main types of receptors. The Chi-arc receptors, spelled TRK, pronounced track, are the good guys. When NGF binds to them, they signal survival and growth.
And the bad guy.
The P75 receptor. It also binds neurotrophins. But if the P75 receptor is activated without a neurotrophin present, or in the wrong context, it actively triggers the death sequence.
It's a literal kill switch.
It is. It's a fail-safe mechanism to prune away useless or incorrect connections. It ensures that only the neurons that are functionally integrated into a circuit survive.
Nature is not sentimental. This leads us perfectly into what happens when this intricate support system fails. Clinical integration.
The classic examples here are, of course, the demyelinating diseases. We built up this whole beautiful story about how important myelin is for speed and efficiency. So what happens when you strip it away?
Multiple sclerosis, or MS, is the big one in the central nervous system.
Yes. MS is an autoimmune disease where the body's own immune system attacks and destroys the oligodendrocytes. You get these patches or plaques of demyelination scattered throughout the brain and spinal cord.
And physiologically, what is the direct result of losing that myelin?
Remember those potassium leak channels? Usually they are covered up by the myelin in the internodal segments. When the myelin is gone, those channels are suddenly exposed. Potassium leaks out massively. The current that was supposed to jump to the next node just dissipates into the extracellular fluid like water from a leaky hose.
So the signal slows down dramatically or just dies completely before it reaches the next node.
Exactly. Conduction block. And because the plaques are patchy and can occur anywhere, the symptoms are incredibly varied and unpredictable. One day, it might be blurry vision because of a plaque on the optic nerve. The next, it's weakness in a leg. And Ganong mentions a classic symptom that ties right back to the physics: heat intolerance. It's called Uthoff's phenomenon.
Why would heat make it worse?
Heat speeds up all biochemical reactions, including the opening and closing of ion channels and the general leakiness of the membrane. If a demyelinated axon has what we call a safety factor of just 1, meaning it's just barely working, taking a hot shower might raise the temperature enough to drop that safety factor to 0.9, conduction fails. The patient suddenly feels weak or their vision gets worse until they cool down.
That's a diagnostic clue right there. Now, what about the peripheral nervous system? There's an equivalent, right?
Guillain-Barré syndrome. This is also an autoimmune demyelination, but this time the attack is on the Schwann cells in the periphery. It's often triggered after a viral or bacterial infection. The immune system gets confused, a process called molecular mimicry, and attacks the peripheral nerves instead of the bug.
And this typically presents as an ascending paralysis, right? It starts in the feet and moves up.
Yes, a classic ascending weakness. The danger, of course, is if it ascends to the diaphragm, because then you lose the ability to breathe. But, and here's the crucial distinction, PNS myelin can regenerate.
This brings us to the whole topic of regeneration. Why can I, cut a nerve in my finger and have it potentially regrow, but if I sever my spinal cord, it's permanent damage?
It comes down to the support cells again, the glia. In the PNS, when an axon is cut, the distal part dies off, but the Schwann cells that made the myelin stay put. They line up and they secrete growth factors, like NGF, and they literally form a guide tube for the sprouting axon from the healthy stump to grow back through. They lay down breadcrumbs.
Come this way. The target is over here.
Exactly. In the CNS, the environment is the complete opposite. It's actively hostile to regrowth. The oligodendrocytes don't guide. They actually release inhibitory molecules, like notogoproteins, that actively stop axon growth. And the astrocytes, they rush in and form a dense fibrous scar, a glial scar, that physically blocks any attempt at regrowth.
So the CNS is wired to prioritize stability over repair.
Precisely. It prioritizes keeping the incredibly complex network from miswiring itself, which could cause things like epilepsy or chaos. It sacrifices regeneration for stability.
One last clinical thought experiment before we wrap this all up. We've talked a lot about potassium. What about calcium? Ganong and Guyton both mention the phenomenon of tetany.
This is a great one because it's a paradox that confuses everyone. Extracellular calcium acts as a stabilizer. It binds to the outside of the voltage-gated sodium channels.
So it kind of holds the door shut more tightly.
Think of it like an extra deadlock on the door. It makes it harder for a given voltage change to pop the activation gate open. The threshold is effectively raised. So if you have low calcium hypocalcemia, that deadlock is gone. The sodium channels become unstable and can open way too easily, sometimes spontaneously.
So low calcium equals high excitability. That feels backwards.
It does, but that's how it works. The nerve starts firing spontaneously without any real stimulus. This leads to tetany-sustained, involuntary muscle contraction. The classic sign is when you put a blood pressure cuff on someone's arm and their hand cramps up into a weird shape. It's dangerous because, again, your respiratory muscles can lock up.
So let me recap that. High potassium makes you twitchy because it messes with the resting potential, bringing it closer to threshold. Low calcium makes you twitchy because it messes with the threshold itself, making it easier to reach.
A brilliant summary. Two totally different mechanisms leading to the same twitchy result.
We have covered a massive amount of ground. We've really built the machine. We established the zones of the neuron: the receptor, the soma, the axon, and the output.
We powered it with the battery, the resting membrane potential, driven by that all-important potassium leak and governed by the Nernst-Goldman equations.
We ignited the spark. The action potential, with its sodium explosion, its potassium reset, and its crucial refractory periods that keep the signal honest and moving forward.
We sped it up with propagation, myelin, saltatory conduction, and the difference between the racing A alpha fibers and the strolling C fibers.
And we looked at the support system and its failures: the glia, the neurotrophins, multiple sclerosis, and the challenges of regeneration.
It really is the ultimate biological machine.
So to bring it all back to the big picture, why does all this intricate detail matter? What's the final take-home message?
I think it comes down to the energy cost. The brain is about 2% of your body weight, but it consumes 20% of your body's total energy budget.
And we usually assume that's because we are thinking so hard. It's the energy of consciousness.
But it's not. The vast majority of that energy is going to one single protein, the Na plus K plus pump. It is being spent hour after hour just to keep the battery charged. Even when you are sleeping, even when you aren't actively thinking, your neurons are furiously pumping ions just to maintain that minus 70 millivolt potential.
The resting potential is not at all restful.
Not in the slightest. It is a state of high, constant metabolic tension. It is the dark energy of the brain. It is an archer with a bow fully drawn, holding it there, burning muscle energy, sweating, just waiting for the moment to let the arrow fly.
And that arrow is the thought, the movement, the sensation.
Exactly. Biology invests an incredible amount of its resources in readiness. The fundamental cost of being alive and aware is the cost of maintaining that ionic gradient, of keeping that bow drawn, always ready to fire.
That is a profound thought to end on. The apparent silence of the resting brain is actually a deafening roar of metabolic activity.
Physiology speaks in voltage, and that voltage isn't free.
Thank you for joining us on this deep dive into the nerve. We'll see you next time when we explore what happens when that electrical signal actually reaches the muscle.
Until then, keep those gradients charged.